Greetings and good day. The topic of this presentation is multi-sensor data fusion integrated with machine learning algorithm for auto-steering of a robotic mower inside berry orchards. The research was carried out at the Leibniz Institute for Agricultural Engineering and Bioeconomy in Potsdam, Germany. The presented study is a part of a bigger project named Sunbot that aims at emission-free berry production. For this purpose, Sunbot project incorporates an electrically driven autonomous tractor with a custom-built mower for autonomous mowing of berry orchards. The project has been funded by the European Agricultural Fund for Rural Development. More information about the project is available at the project website at www.sunbot.de. Here is a simulation video to show an overview of the automation work package of the project. It should be noted that the articulated steering electrical vehicle shown in the video is the final vehicle that was purchased for the project and not the experimental mobile robot that we used for the presentation. The objective of this study was to develop a collision avoidance toolbox for Sunbot electrical tractor. For this purpose, we used a four-wheel steering mobile robot platform for experimenting and validating the proposed hardware and software. This step was necessary to come up with a final solution for the main electrical tractor. To be on the same page, let's look at the overview of a general collision avoidance system. As it can be seen from the slide, we have an orchard tractor that is required to autonomously navigate inside plants row, while at the same time manage to be in the center of the row and avoid obstacles on the front, left, and right. These obstacles include random objects, human, animals, and bush support. For this purpose, we need a set of reliable sensors that can measure the distance between the vehicle and its surroundings at a minimum rate of 10 readings per second. Based on these measurements, an error signal is generated by comparing the desired distance and actual distance between the vehicle and the obstacles. The main objective is therefore to drive that error to zero. Here is a simple closed-loop feedback control system that shows how the process of controlling the vehicle based on the generated error is carried out. The sensor shown here is responsible to measure a distance between the vehicle and the obstacle. A Jetson Nano computer with a control algorithm that can be PID, fuzzy knowledge-based, or machine learning algorithm does the computation. This is called the controller, which outputs control signals directly to the actuators such as electro-hydraulic valve or to an industrial controller such as Hyduck TTC 580. Which is responsible for vehicle control. Some of the main challenges of the research can be summarized as follows. Berry orchards have unstructured plant row boundaries. Outdoor conditions such as light levels, debris, high-density bushes, and other natural disturbances can cause noisy measurement on sensors or even false readings. Harsh environment, such as rain and sun, can interrupt the central automation system. The pictures below show geometrical variation in the rows and high-density bushes, as well as the presence of random stems and leaves that can block the sensors or be treated as obstacles. For the purpose of autonomous navigation, a commercially available GPS-based navigation toolbox was purchased and installed on the mobile robot platform. It should be noted that the purchased navigation toolbox did not provide obstacle avoidance features, meaning that the robot could have collision with random obstacles while doing autonomous navigation. The task of autonomous navigation also needs to account for GPS denial environment. Results of our preliminary studies and experiments and field evaluations have shown that the performance of the available GPS navigation toolbox can be interrupted due to GPS receptions or the issues with IMU calibrations. A proven solution to collision avoidance is the use of LiDARs. Although high-end LiDARs are widely used for obstacle avoidance, but they add extra cost and maintenance to the vehicle, which makes the final system too expensive to be used by farmers. In addition to that, a decision was made in the Sunbot project kickoff meeting to develop an alternative sensing solution that replaces with high-end LiDARs. The video below shows the collection and assembly of 3D LiDAR point cloud on the four-wheel steering mobile robot platform, visualized in ROS RVs. The data is captured using a Velodyne VLP16 LiDAR and georeferenced based on RTK GPS and odometry information. The main objective The main objectives of this study can be summarized as follows: to produce the error signal and then to drive that error signal to zero. The focus of this presentation, however, is on the very first objective. For this reason, we had to design and develop hardware and software for basic obstacle avoidance tasks of the robotic mobile platform that has the main following features: modular ECUs, distributed control system, ROS-based software, and the communication between ECUs were designed to be serial and CAN bus. Here is an overview of the experimental mobile robot platform with an installed RTK GPS Navibox and the proposed collision avoidance system, including multi-channels, short-range infrared sensors, and long-range laser sensors for distance detection. Here is an overview of the multi-channels infrared sensors that was installed on the left and right side of the robot. Each of the sensor modules were programmed separately to act as a ROS node, in a way that raw measurements and processed data were published on ROS as a float32 multi-array message. For the front of the robot, we used 3 long-range time-of-flight laser sensors for distance detection. The base sensors were TF Mini Plus, manufactured by Benowake, with maximum distance detection of 8 meters. Each sensor was programmed to send measurements below 2 meters. Each of the sensors were placed on a servo motor to scan the environment within 30-degree rotation angle. The sensors controllers were designed in a way that outputs could be transferred to the ROS computer via USB and CAN. For the sensor controller, we used the high-performance Atmega 2516 microcontroller with 16 MHz speed, 256 KB of flash memory, and 4 UART. Here is a short video demo of the front sensors mounted on servo motors scanning for obstacles. The following computers were used in the collision avoidance toolbox. The industrial PC model Histon Fanless Core i5 was used for running simulation experiments in MATLAB and CuPiliaSim, previously known as VREP. The NVIDIA Jetson Nano was used as the main collision avoidance controller, on which ROS was running and all control algorithms were implemented. The Raspberry Pi Model 4 was used as a final sensor ECU for logging raw sensors data and for applying filters and pre-processing of the raw sensor data. For the purpose of troubleshooting and validating the hardware and software, we conducted several tests, including laboratory and field tests under different light conditions, indoor and outdoor, tests for the reliability of the hardware architecture and wire connections, and data collections for development of filters and control algorithms. Here is the schematic of the final communication architecture between ECUs, showing that all sensors data are transferred to the obstacle avoidance computer via daisy chain CAN bus network. The data are then processed by the control algorithm that is implemented as Python codes. The control signals are then transferred to the GPS-based navigation toolbox via Ethernet cable. This slide shows the screenshots of the two software, including PCAN View and Adaptive Agritech Multiport Manager, that we use for directly connecting raw data from the sensors under Windows and Ubuntu. The two software made possible cross-platform logging of all sensors data via CAN bus or USB serial. We have been working on designing three controllers, including PID, fuzzy knowledge base, and a supervised machine learning algorithm. We also designed experiments with the null hypothesis that the performance of these controllers are the same. We have managed to receive preliminary results of the PID and fuzzy knowledge base controller in the simulation environment. The experimental results for the supervised machine learning algorithm is a work in progress. This slide is only intended to show the overview of the proposed architecture for the machine learning controller. Here, the controller receives inputs that are distance measurement from 7 multi-array infrared sensors and produce a steering and speed based on the previously trained dataset. For this approach, an expert operator will manually drive the robot inside the road using remote control and collected data. These data are then used to train the machine learning controller and to navigate the vehicle. This simulation demo shows performance of a simple P controller in the Copilot sim environment on the 4-wheel steering mobile robot. This demo shows performance of a simple P controller in a simulation environment on an Ackerman steering tractor, but with the same sensor setup. The objective of this simulation was to test if the proposed sensing system can be used successfully on different robotic platforms. For the fuzzy knowledge-based controller, we created 3 different test tracks in the simulation, including circular shape, oval shape, and a 90-degree angle track. The idea was to tune the parameters of the controller in a step-by-step approach. The same experiment setup will be created for actual field test with the actual robot. This video demo shows the performance of the fuzzy knowledge-based controller in the simulation environment for the circular shape track. This video demo shows the performance of the fuzzy knowledge-based controller in the simulation for the oval shape track. And here is a summary of tests with the mobile robot in the simulation environment for the 90-degree angle track. Here are the plots that compare trajectory responses of the collision avoidance and manual drive controller with respect to the desired response in the oval shape track and the 90-degree angle track. It can be seen that in both cases, the collision avoidance controller has performed a better task than the expert operator manual drive. This slide shows the plots of the sensing and control output resulted from the simulation study inside the oval shape track and the 90-degree curve track. The difference between the obstacles in the left and right sides of the robot in the two tracks can be clearly seen from the plots of the infrared sensors. It can also be observed that the controller has maintained the minimum allowed distance between the left and right side of the robot and obstacles for each track, which were 0.4 meter for the oval shape track and 0.1 meter for the 90-degree curve track. The control output for both experiments was proportional to the steering angle of the real robot and varied between minus 0.22 and positive 0.22, corresponding to minus 22 and 22 degrees. This table summarizes the performance of the controller at different speeds in the 90-degree curve track experiment in terms of the fastest time to complete the track and the success rate between 10 repetitions. It can be seen that the controller failed at a speed of 40 km per hour, which is 4 times faster than the actual robot speed. For the speed between 5 and 35 km per hour, the combination of the infrared and laser sensors with fuzzy knowledge-based controller resulted in 100% success rate. While these results were entirely achieved in the simulation environment, they can provide a valid estimation of what should be expected from the real-world scenario. This is a video demo of testing the robot hardware and software inside real berry orchard and data collection. This presentation reported on the design of a distributed control system with multi-sensor data fusion and a fuzz knowledge-based algorithm for collision avoidance of a four-wheel steering mobile robot. The objective was to stabilize the robot in the presence of an obstacle by enabling it to navigate from a starting point to a goal point in the shortest time. This was achieved by a control strategy that reduced the error distance between the sensor readings and a minimum allowed distance with the left, right, and front obstacles. To analyze and test the robustness of the controller, 2 simulation studies were performed in 90-degree curve track and an oval-shaped track. In addition to that, full experiments were carried out with the actual robot to test the hardware and the reliability of the communication between ECUs. The result of the study can be used as a proof of concept for the successful use of the proposed perception setup, which is a multiple low-cost distance detection sensors as an alternative solution to high-end LiDARs for collision avoidance of mobile robots inside unknown environments or GPS-denied environments. The next slide shows a summary of the work in progress for the machine learning algorithm and the lessons learned from the experimental platform for installing the collision avoidance system on a main Sunbot electrical tractor. Please note that narration has not been added to the next slide.